Okay, hi. So the first speaker for this session is going to be Yogesh. The first speaker for this session is going to be Yogesh. He'll be presenting some lower bounds for polynomial calculus over non-Boolean base.
So yes, I'll tell you about some results in proof complexity, and specifically about polynomial calculus proof system. So this is joint work with Veena at IMSC and Shashank at IIT Indore, and it will appear in SAT. So let me start by telling you what proof complexity is. So proof complexity is study of complexity of proofs of tautological Boolean formulas in formal proof systems, where a formal proof system can think of it as, given some axiom and inference rule, you want to derive all possible tautologies. Okay, and we'll restrict our attention to only propositional tautology, and we're only looking at fragment of proof complexity, which is propositional proof complexity. More formally, for us, a proof system, a propositional proof system will be one where you can derive every possible tautology, and if it derives something, it must be a tautology. That is, it must be sound and complete. And the second property that we would want out of our proof system is that the proof should be efficiently checkable. Okay, so if you have a if you have a S size proof, then in S to the order 1, we should be able to efficiently check whether the proof is a proof or not. Okay. And we'll call a proof system polynomially bounded if for every tautology we have a proof which is polynomial in the length of the tautology. Such a proof system we'll call as polynomially bounded proof system. So this is a setting of proof complexity, and we'll tell you about some motivation why we study proof complexity. The main question in proof complexity is this NP coNP question. It was observed by Cook and Reckhow that if there exists a polynomially bounded proof system, then that would imply NP equal to coNP, and the other way around also exists true. So one direction one can see easily, because if you start with tautological Boolean formula, they form a coNP complete language. And if we can find a polynomially bounded proof system, then coNP will sit inside NP, and therefore coNP will be equal to NP. And similarly, if NP is equal to coNP, you can argue that we can construct a polynomially bounded proof system. So this is the first motivation for studying proof complexity. And either you find a proof system which is polynomially bounded, or you prove lower bounds for stronger and stronger proof system in order to gain evidence towards NP not equal to coNP. So that's the first motivation. The second motivation is lower bounds on the length of the proofs in a particular proof system translates to lower bounds about runtimes of classes of algorithms. For example, if you know about resolution proof system, lower bounds in resolution imply lower bounds about runtimes of satisfiability algorithms. And if you know about sum of squares and Shirali-Adam proof systems, those proof systems tell us about limitations of linear programming and semi-definite programming based algorithms. Okay, so it's a nice way to prove limitation of classes of algorithms. Okay. The other motivation is, by proving lower bounds in proof complexity, we can also end up proving lower bounds in other proof systems. For example, weak proof systems like resolution and null signatures can give you monotone circuit lower bounds or monotone span program lower bounds. And stronger proof systems like ideal proof system and cone proof system imply lower bounds for circuits. So in that respect, studying proof systems is important. And I guess most importantly for us, and we can prove unconditional lower bounds. So we do it. So there's a motivation for studying proof complexity. So let me now tell you example of a proof system which is more closer to what you see in a logic textbook. It's a Frege proof system. So you have a bunch of axioms and a single inference rule, which is this modest ponens. And using this axiom and this inference rule, our goal would be to derive all possible tautologies, and in the process study the complexity of proofs. So as you can, this is closer to reality, and you can guess. We are far from understanding it. For example, we don't know whether Frege is a polynomially bounded proof system. So we don't know this. So we don't know lower bounds in Frege proof system. So what we do is we study restrictions of Frege. Okay. By restriction, I mean you restrict the complexity of each line. Okay. If you restrict each line to be just a clause, you get a clause Frege. You restrict each line to be AC0 circuit, you get a AC0 Frege, and so on and so forth. NC1 Frege is where each line is just a polynomial size Boolean form, and that's what we call the Frege system. Okay. So we have lower bounds for some of these restrictions, and we don't have lower bounds for some others. Okay. For example, clause Frege is a resolution system. We know everything about it. We have lower bound for AC0 Frege, but we don't have lower bound for AC0 P Frege, for example. And ultimately, we want to understand Frege.
So AC0 P Frege. So in deciding what to do, what next line to write, you are allowed to evaluate a AC0 so mod.
No, these are structural manipulation. You have some circuit, other circuit, and then there is some rule which says that you can derive some other circuit using it. There will be some rules in a Frege proof system.
Yeah.
There are lines are AC0P circuits, and then using these lines, you are deriving new lines. You are modifying something, and you will derive new lines. For example, here I'm saying A implies B implies A. That's an example, right? So I can replace these A's by some AC0 circuit, B by some AC0, and this will be a true thing. And then I can use modest exponents to derive, something new, some new AC0 pieces. So we are stuck at this AC0P Frege restriction, and it's a major open problem to prove AC0P Frege lower bounds. What is this? AC0P is bounded. Okay, bounded depth is a unbounded additive. These are circuits with OR, and not, and mod components. And generally, the progress in proof complexity has mirrored progress in circuit complexity. The only exception is this AC0P Frege. Because the lower bounds in circuit world for AC0P class goes through algebraic techniques, and we don't know how to make those algebraic technique works in the proof complexity. Okay. So that's why we are stuck at this AC0P Frege class. And because of this motivation of proving lower bounds for AC0P Frege, Clegg, Edmonds and Impagliazzo introduced this algebraic proof system, which is known as Polynomial Calculus proof system. And actually, it's not a proof system per se; it's a refutation system. So instead of a tautology, you start with the negation of a tautology, which is an unsatisfiable formula, and you prove a contradiction of it. So in polynomial calculus, we start with an unsatisfiable polynomial system, and our goal will be to certify that this system is indeed unsatisfiable. Okay, and the rules are very simple. You can multiply your polynomial by variables, or you can take linear combination of your derived polynomials. And if you can derive one polynomial, then you can definitely be sure that your system does not have any solution, because any common root of your system will also be root of each of the line in your proof. Okay. So soundness is obvious, and the completeness part follows from this Hilbert-Nullstellenschaft theorem, which says that if your system has no solution in the algebraic closure of your field, then the one is in the ideal generated by your polynomial system. Okay. And don't worry about this algebraic closure of the field, not the field. It can be taken care of. For us, we'll always have some constraints which will force a solution to be inside the field. Okay. So it's a complete proof system and sound proof system. And these are the two size measures that we studied. One is the size measure. These are the complexity measure that we studied. One is the size measure, other is the degree measure. Size is just size of each line. Each line is a polynomial, and size of polynomial is number of monomials. Okay. For infinite field, we also have to take care of sizes of coefficients and ignoring that part. The degree is maximum degree among all possible polynomials. So as I said, this polynomial calculus proof system is proof system for unsatisfiable polynomial systems, but one can use this for CNF unsat problems as well. One can encode unsatisfiable CNF formula using a polynomial system, and then one can start from there. Okay. It's a very simple encoding. 0 represents false, 1 represents truth, and then there is standard encoding which people might have seen some. Okay. This is an example of DC proof. You're multiplying by variable, doing some subtraction, some additions, and finally you're deriving the one polynomial. Okay. So what do we know about this polynomial calculus proof system? So one of the important thing that we know about PC is that there exists this degree size relation, which says that if you have a small size proof, then you can derive a small degree proof out of it. If you have S size proof, you can derive degree square root of n log s size proof out of it. Okay, so this is a nice result because now this gives us a way to prove size lower bound. If you can prove a degree lower bound, you get a size lower bound. If sufficiently strong degree lower bound will imply a size lower bound, right? And we have degree lower bounds from a lot of codes for all kind of different formulas, random CNF formulas, Digital principles, and many more. Okay.
There's also like global basis that complicated like about how what kinds of global basis you can get. Because the operations look similar to what is allowed.
The operations are just generating
All,
things.
all the integrate any element in the idea.
Yes.
Yeah.
That's all.
But there is no basic, but you're not trying to get to any specific kind of. You just want to get to one.
Just an adaptive form of Hilbert motion.
Yes.
Hilbert motion is a static sheet.
There also improvement with you put the form like into the same form to get H into a specific form where taking membership. But that's just one way of it.
Okay.
The same linear degree because you have some Boolean constraint.
The Boolean constraint will always be low.
So x is square equal to x is the maximum degree can be n. That's the reason.
Yes. You can always reduce, always work with multiple. So we know linear degree lower bounds, and using degree size relation, we know exponential size lower bounds for this. So it seems we have a very good understanding of PC. But I want to say that our understanding is not robust. Okay? Just slight variations to PC, and we don't know how to do lower bounds. So let me give you one example. Consider PC where truth values are now encoded using plus minus 1 instead of 0, 1. Okay? So truth is encoded by -1, false is encoded by +1. And in this setting, we don't know how to do lower bounds until very recently. And this is just a fine shift, right? This is just a fine shift of variables. If you change your xi variables to 1 minus yi by 2, you will get a proof in this plus minus 1 code. Okay? So degree does not change. Degree remains same in both the settings, but size might change. Okay? And in this case, we don't have any degree size relation. That is the reason why we don't have, one of the reasons we don't have size lower bound for PC plus minus.
Just one thing, so the degree size of polynomial calculus.
Yeah.
is also derived using the 0-1 polynomial calculus.
Yes.
But it's derived using some sort of restriction.
Restriction.
And that's why it's +1 minus 1.
Yes. Yeah. Let us say next slide. I'll say
Oh.
this.
The size is the number of lines. What is the size?
Size is like size of each line, you add them up, and size of each line is number of monomials you get from. And I just want to give you what, and as Arkadev said, there is no degree size relation for PC plus minus 1 because the degree size relation looks like this, and this is how we prove it. We collect all the large degree terms, and then we kill them by setting variables to 0 and obtain a small degree proof. Okay. Now this kill step cannot go through because 0 does not exist in our domain, and plus minus 1 cannot kill large degree terms. So because of this simple reason, we now don't have size degree, right? And for good reason this is the case, and we cannot prove generic size degree relation because there is an example where we have a linear degree lower bounds in PC plus minus 1, and but we have polynomial size proof for such formula. And that formula is citing formula. I just want to skip this example because in interest of time, but the Citon formulas have linear degree lower bound, but they have polynomial size proof in PC plus minus. So this says that there is a linear degree lower bound. And it's a very simple exercise to convince yourself that there's a polynomial size proof in PC plus minus. So what do we know about PC plus minus? As I said, until recently we had no lower bounds in the system. Sokolov in stock 20 showed first lower bound in this setting, showing that for random order 1 CNFs with high probability with an exponential size, Pigeonhole principle will have extended for side of PC presence. And among other results, he also showed a lifting result, saying that one can lift a degree lower bound in some other proof system, which is sum of squares, to a size lower bound in PC presence. Okay. And now we can use degree lower bound from sum of squares to size lower bounds in PC presence. But there is a catch. I mean, this only works over reals. This result of the 15 results only over real fields. And he left this as an open problem, to prove lifting results for PC for arbitrary field, lifting degree, PC degree itself to a PC size using some suitable gadget. Okay.
So this means that every variable is now majority of some other variable.
Yeah, exactly. Majority of the variable. That's a gadget. We have to use that. And this is so this is our result. We show that PC degree can be lifted to PC size using 1-bit indexing gadget. Okay. Building on Sokolow's, a lot of techniques that we use are from Sokolow's. Our observation is that indexing can do the job, which majority was not able to. And this 1-bit indexing function is, there are these 3 variables that
No, so your result is that it works for any field.
it works for any field.
That is the
No, but we are also lifting PC degree to PC size. We were lifting SOS degree.
Oh.
And also in terms of parameter, also we are getting exponential in D. He was getting exponential in D square by n. So he needed SOS degree to be at least square root n to say something. We can say non-trivial considering it's only.
They're going from degree
We're going from degree
D
to
the same
size.
system,
Uh,
or in degree or the size of degree system. This is the
But importantly, when the formula is lifted,
Yeah.
not only unlifted.
Degree of unlifted goes to size of the lifted function. Degree of H will go to size of H lifted with indexing.
Yeah. This is for different, but it's lower, but this is not a significantly more complicated formula loading.
It's a 3-bit.
Yes.
Yeah, so one of the corollaries like for random 3CNF formulas, lifted with 1-bit indexing, they get with high probability of exponential size.
So for random formulas,
Yeah.
it is not known whether the size of a random formula is the polynomial calculus is large.
Plus size.
Yeah.
The first theorem of Fokker. We showed it.
Or you're, no, but that was a lift.
No. First, he also showed for unlifted formulas also. And then he had a lifting result as well.
But maybe not the 3, but some large scale.
Some large,
Still
some 20 or something. Yeah. Some remarks like it works for arbitrary field, and then there are cases.
But is there some density type that you have to have some like random case at a certain density, number of clauses or number?
Yeah, that will be there to ensure that it's unsatisfiable.
But that's it, like.
And
just-
some other properties one has to satisfy so that his proof goes through. Right? To
But it's
require
for
more
other-
structural arguments from your random single formulas. And for that, we're going beyond. Otherwise, 3 would be enough. If we choose density large. Yeah, so there are, the second remark I would make is that there are obviously formulas where SOS degree is constant and PC degree is linear. In such cases, you won't get, size lower bound using earlier results, but in our case, you can get lower bounds. Okay, so let me move on to the second setting of our results, which is this PC with extension variables. So we have our unsatisfiable system, which is this even to P1, and there are these range extras. And apart from these, we also have these extension variables, which are giving names to some polynomials. Okay, these are these name variables, which is saying that Q1 I can replace by Y1, Q2 I can replace by Y2 and so on and so forth. Okay. So in forefront, we'll define these extension variables, these new extension variables, and then we would start deriving 1 equal to 0, starting from all these examples. Okay, this is the setting of PC with extension variable. You're allowed to choose your extension variable beforehand, and then you start from there.
This can be size.
This can reduce size because a large polynomial Q1 can become Y1 and they can work with Y1 going ahead. And the first observation in PC plus minus is nothing but a special case of PC with extension variable. Substitution can be done in PC very easily. Right? If we choose following extension variable, just saying that yi is like 1 minus 2 xi, and I can do the substitute. I can substitute xi as 1 minus yi like this. And starting from a 0-1 encoding, I can derive a plus minus 1 encoding. And then use a plus minus 1 proof to prove 1 equal to 0. Right? So PC plus minus 1 is a special case of this PC with extension. So what is known for PC with extension variables? So recently, Impagliazzo, and Pitasi and CCC, when they showed that PC over finite fields, it's important, it's only over finite fields. Well, we don't know over real in simpler cases. But over finite field, they showed that if you allow some quadratic number of extension variables, each having log n arity, then you can show exponential size 1. That's what they show. So what we do in our results is we improve the parameters. We also work in PC over finite fields with subquadratic number of extension variables.
The
Number of variables, it depends. So yes, so we are in the same setting, PC over finite fields. Number of the extension variable is also same, subquadratic number. But our each extension axiom is poly size and it can depend on poly fraction of variables. So they can be 1 minus. It's almost all but one. All. And this poly size is not a restriction. You can see, it's a restriction, but it was present in previous result also because arity was only log n. The size was only poly there also. Okay. But there is a catch, and there is a drawback to our result. Our result is not for a CNF formula. So it won't imply lower bound for CNF unsat language. But it does have a small AC0 P circuit. So it does, so we do have lower bound for some small system of AC0 P.
So even the CNF formula encoding will be very large.
CNF encoding will be large for our formula. But it has small AC0 P circuit. A small size and small depth. P4.
Sorry, and PC over the finite field would be the characteristic of the finite field would be not equal to P, right? And yes, your exponential go on.
Yeah.
So I mean, you're saying for PC over finite field.
Yeah.
So the characteristic of the finite field.
Yes.
Over which to carry out the PC, it's not the same as P, right?
Correct.
That's important.
Okay. I want to tell you some details, but okay, so let me not define all these. Directly tell you the idea, high level idea of the lifting result. This is the template which was present even in 0-1 case. Let's see the template. So you start with a small size proof over PC plus minus 1. Okay. And then you collect these high quadratic degree pairs. So you're collecting these pairs Q1, Q2, so T1, T2, such that this T1, T2 should be present in the same line. Okay. And the condition that we are putting is that degree of the product of these terms must be large. Okay, we are collecting all such pairs. Okay, and we are saying that all such pairs which have large degree, you collect all of those. And our idea will be we would try to reduce this measure. Instead of reducing degree, we would try to reduce this quadratic degree measure. Okay, and the idea will be same. We'll choose some variable which is more popular in all these pairs, and then we want to do some operations such that we get rid of all the pairs which have X in them. Okay, but there is a catch there. I mean, to apply that operation, we would have to ensure some preconditions, and that's where we will exploit the fact that we are working in the lift, and we can do some restrictions to ensure those preconditions. Okay. Then the process will go through. We'll end up making this quadratic degree measure small, and then there is a result of Sokolov, which says that if you have a small this quadratic degree measure, then you can convert it into a small degree measure, and then you can use degree hardness, okay, to say size is right. That's the high level concept. And this, I didn't define this properly, this quadratic degree here, but I just want to say that it might find application in other settings.
Yeah, true question. How does this skill step happen? But there's no zero one, right?
It's some operation which is not setting things. It is some structural operation on the proof, which would get rid of all these bad pairs. It's not a restriction operation. But to apply this, you would have to do some restriction to meet the condition such that this operation can be done.
It's one operation that is going to get rid of many arbitrary variables.
It will, and this operation which can get rid of, it depends on the variable that you are applying. It depends.
So you can take a variable that appears in many
That appears in many quadratic pairs, and then do some operation with that variable in mind. And if you do that operation, all these terms with that variable in them will vanish. That's how we end up reducing this measure.
And you said even T2 in QI, that is even T2 are term.
T1, T2 are terms, monomials, in the same line.
Same.
We're just taking cross thing. Because small quadratic degree of a polynomial means that all monomials are kind of same. There is more intuition to it, and I would say that people look into this measure because it might find application as well. So this is the idea about the PC with extension variable result. Let's wrap it up. So I mean there are the two things. One is that we extend the result of Impagliazzo and Pitassi to allow for log n degree instead of log n array. That's the first thing. For some formula, we make sure that we can do this. Right? Okay. The second thing is we, inside the usual step, we do XOR left so that we can handle poly-size extension array. Because we can do some restriction to convert those poly-size extension axioms into a log n degree. And then we can apply our idea 1 to handle the log n degree. It's a very high level. So let me conclude. So we have these two results. One is this lifting results over PC plus minus 1, lifting PC degree to size. And then we improve parameters for this other section, which is this PC with extension.
Yeah, so this operation that you will do.
Yeah.
So what sort of an operation? You said it's not substitute.
This is the operation. So you write each line, and you take the part with extend, and you take the part that does not have extend. And you write each line like this, and then you place these two polynomials in different lines.
So
And then this
QI, you will have QI 0, QI 1.
Yeah, so all those, pairs which had X in them disappear, right? But now you would have to argue that this indeed is a valid proof of your formula. You can do any operation, but it has to be a valid proof. And we can do that if we.
And that's why you have to go to quadratic. You can multiply it.
And yeah. Yes.
Yeah, so this 1 minus 1 can be replaced by any arbitrary element in the field, right?
So that is the thing. If you can't, we don't know lower bounds. For example, if you encode things using 1 and 2, you don't. It's still very robust. I mean, it's still our understanding is not that.
It just works for 1 minus 1.
1 minus 1 because the ideals in X square equal to 1 to the binomial thing. With 1 and 2, those things won't be binomial. Those constraints, the range constraint won't be binomial. We have to put them to other things.
What is the
Two monomials. In a polynomial, there are two monomials. It's a binomial.
X2 minus xi square minus xi,
That's a binomial. And xi is equal to 1.
Polynomial. If you start with a polynomial that has xi squared term and you apply this operation, it only simplifies.
It doesn't blow up size and degree. But if you have 1 and 2 in your domain, then this can blow up size.
It seems very explainable. It is like this is somehow like you haven't stumbled upon the right way of coding these programs. Like the right code should be over.
So why is this thing, it's very strange.
I mean, by split operation, what is the other two?
Yeah.
The initial system does not contain.
Oh, does not, original H did not contain.
I mean, it says that split will produce valid proof only when your system does not contain X.
So Q1.
And this can be ensured using indexing gadget because we can make one of the variables irrelevant.
Circuit drive, circuit drive.
Yeah, it goes to formula again. I got it from
Let's start.